The James Webb Space Telescope is our most modern and advanced space telescope. Its main purpose is to look for the oldest and most distant galaxies, which are so redshifted by now that their light arrives not as visible light, but as infrared. Alright, so you design that thing and build it and test it and redesign it and test again. For like 20 years and with a $10 billion price tag. And then you finally shoot it into space.
And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
And put it where? Where do you park a thing like that? There are many different things to take into account here. It needs to get there, it needs to stay there, it needs to communicate back with Earth, and most importantly, it needs to be blocked from all the infrared light that we do not want to observe. Like, what do you do here on Earth when you want to watch the stars? Well, starlight is faint, so you need to get rid of all the other light around you. First and foremost, you need to block the sun and the bright glow of the atmosphere caused by the sun, aka the blue sky. So you wait until the sun is blocked by Earth, aka the night. But even then, when you're close to a brightly illuminated city, this will mess up your observations a lot. So you need to get rid of all the secondary sources of light too. And the same goes for JWST. Actually, the main part of its body is a radiation shield to block out the infrared light from the sun. But also, it needs to block out the secondary sources of infrared light, the planets. In this case, mostly Earth and also its moon. So eventually, we put JWST in a location where it would always be in a straight line away from the two brightest infrared sources, the sun and the Earth, and about 4 times as far from the Earth as is the moon. And what's there? Nothing. Just a point in space. A very particular point in space, though. At the risk of stating the obvious, but space is a very different place from Earth. For one thing, once you put an object into space, it will not simply stay in place because of a thing called inertia and another thing called gravity. And while these also exist on Earth, they are especially tricky in space because you have no friction at all to restrict motion. Also, gravity means that everything attracts everything else all the time. So things in space tend to move around a lot. What happens when two moving bodies attract each other? Well, 2 things at once. First, they do continue to move straight ahead, but also they move towards each other. So in total, you get a curved path. This means if they're moving fast enough, they will attract each other and move towards each other for a bit, but then move off again into deep space. If they're slow enough, they will move in so-called bound orbits, Kepler ellipses, with the center of mass in the focus. And that means that any object in space is either moving away into infinity or it orbits something. Orbiting objects move on ellipses around the common center of mass. The center of mass is situated between the two bodies according to their masses. If both masses were the same, it would be smack in the middle, and if one mass were larger than the other, it would be closer to that mass, etc. For example, the Sun is much more massive than the Earth, by a factor of around 1 million. In fact, more than 99% of the mass of the solar system is just the Sun. So the center of mass between the Sun and the Earth is so close to the center of the Sun that it's within the Sun. If one mass is much bigger than the other, then effectively the smaller mass orbits the larger one. But technically they still both orbit the center of mass. Okay, but what if you have more than 2 bodies, for example 3? Even though this 3-body problem looks like just a simple variation of the 2-body problem, it turns out that there is no general solution. And most results are just pure chaotic motion. Well, if you paid close attention, I did say no general solution. There are some solutions for special cases though. One of those special cases is the so-called reduced three-body problem, where we have two large masses and a third mass that is so small in comparison that its gravitational attraction can be ignored. In the following, I will mostly use as an example a star plus a planet plus a spacecraft. But remember, it could be any two other large masses and a third distinctly smaller one. So in simple terms, we have a star and a planet moving just as in the well-understood two-body problem, and we have an additional spacecraft which is just moving in the combined potential of those two, without influencing them back. And that's something we often do in physics. If some problem is too complicated to solve directly, we take a simpler problem that is similar, that we can solve, plus we add some perturbation on it to represent the more complicated situation. So we can use what we already know and just build on that. Alright, so let's solve the restricted three-body problem. To simplify the motion of stars and planets, first let's switch to a frame that is rotating along with them. Now, any points that rotate together with the two bodies are stationary in this reference frame. This means they always stay in the same position relative to the star and the planet. So we can write down the expression for the forces in the system, taking into account all the symmetries of the system and also that it's rotating. And then solve for the stationary points. There are 5 solutions, and these are called Lagrange points, L1 to L5, because these were first described by mathematician and astronomer Joseph-Louis de Lagrange. The first 3 can only be calculated numerically or approximately, while L4 and L5 have exact solutions. L1, L2 and L3 all lie on a direct line passing through star and planet. L1 and L2 are situated symmetrically around the planet, with L1 towards the star and L2 away from it. L3 lies on the other side of the star, almost at the same distance as the planet, just a tiny bit farther out. The 2 remaining points, L4 and L5, are 60 degrees ahead and behind the orbiting planet, at the same distance from planet and star. When we plot the effective gravitational potential of the rotating system, we can see why the Lagrange points are where they are and what the surroundings look like. And from this potential we can also see what makes the Lagrange points so special, even though there's literally nothing there, they're just points in empty space. Because the potential isn't about where you have objects, well, just indirectly. It is about where you have forces. And at those plateaus where the potential is flat, at the Lagrange points L1 to L5, you have no force. And if you have no forces acting there, then things that are there will stay there. And yeah, that's the reason why the JWST sits at Lagrange point L2. Okay, so far the Lagrange points have just been a solution that fall out of an equation, and which is fine, but we can also try to understand them more intuitively. And for this we need 2 simple facts from the two-body problem. At any given distance to a star with a certain mass, there is a specific velocity for a stable orbit. First, orbiting objects move faster the closer they are to the star. And second, if you keep the distance equal but increase the mass of the star, this velocity also increases. Now, let's consider the spacecraft at L1, and just for a moment let's switch the planet off. What would the spacecraft do? Well, it's on an orbit closer to the star, so it would move faster than the planet on its orbit. But if we switch the planet back on, its gravitational attraction means that effectively the gravitational pull from the star is reduced, because the planet is pulling in the opposite direction. Basically, this is the same as reducing the mass of the star, meaning reducing the spacecraft's velocity. So on the one hand, the spacecraft speeds up because of the smaller orbit, but on the other hand, it slows down because of the planet's additional pull. At L1, these effects exactly cancel out each other, and the spacecraft has the same orbiting velocity as the planet next to it, meaning it will always stay in the same place with respect to the planet. For L2 and L3, we can use the exact same logic like we just did to see why these points are stationary too. L4 and L5 are a bit more subtle. If you apply the two force vectors from star and planet at L4, the resulting force vector will point exactly at the center of mass. In the rotating frame, this will exactly cancel out the centrifugal force, meaning these points rotate around the center of mass exactly like the planet and the star. And that's how we can understand the Lagrange points at a more fundamental level than just being the solutions of an equation. Okay, finding a mathematical solution is one thing, but an equally important question is the solution stable? Will it persist over time? We can also calculate that. Well, L1, L2 and L3 are not stable, just metastable. This means that small perturbations from other masses or slight imperfections in their course will make objects drift off these points, not immediately, but eventually. However, for spacecraft trying to hold position at one of those points, that's still a win, because those points are mostly stable, so the required course corrections are only minimal. L4 and L5 are actually stable, as long as the mass ratio of star and planet is at least 25. If you're a physicist or you at least understand how potentials work, this will make no sense to you at first glance. As in the potential picture, L4 and L5 are situated on a local maximum, which should mean they are unstable. The thing is though that we are in a rotating reference frame and the potential is velocity dependent. This picture only applies to stationary objects in the rotating system. As soon as an object begins to move, the potential will change. In fact, objects around L4 and L5 will experience a Coriolis effect that will force them into a bean-shaped orbit around those points. This means that planets often collect dust or rocks or even full-sized asteroids at those points. The most famous ones being the thousands of asteroids preceding and following Jupiter. They are respectively called Greeks and Trojans, named after Homer's Iliad. Two of Saturn's moons even have smaller moons at the L4, L5 points of the respective Saturn moon systems. The inner planets, like the Earth, have fewer Trojans because they are too close to the Sun, and the massive gravitational effect of the Sun is destabilizing these objects. But yes, there are a couple of asteroids following the Earth at these points currently. One of those runs in the so-called horseshoe orbit, meaning it oscillates between L4 and L5 via L3. Okay, that's amazing. Does that mean that the JWST is just sitting at the Sun-Earth L2 point, doing nothing, just chilling? Not quite. It orbits around L2 in a so-called halo orbit. This orbit is quite large actually. It is comparable to the orbital distance of Moon and Earth. So the JWST isn't at L2 in the same way the Moon isn't at the position of the Earth. This was done because it is easier to establish and also maintain than just sitting at a point, and also because the instruments on JWST are actually solar powered, so it should never enter into the shadow of the Earth or the Moon. Its orbit looks mostly elliptical from the front and above, but from the side you can see that the ellipse is tilted and also has a small three-dimensional curvature. So it's kind of a bent ellipse. We've already said that the position at L2 is only metastable, so that means you have to do regular course corrections for station keeping there. The JWST is actually orbiting a bit too far in from L2, so it will constantly wander inwards back towards the Earth, then correct again a little bit back, just short of L2, etc. That's a bit like Sisyphus trying to push the boulder up the hill, only for it to roll back down again before reaching the peak. And actually, if the JWST ever overcorrects beyond L2, it will drift off into deep space, lost forever. Anyway, the JWST does these course corrections every 3 weeks, and it has enough fuel to continue doing that for around 30 more years. Okay, hopefully you now have a better picture about what Lagrange points are and why they are useful, and also what the JWST is doing there. If you enjoyed this video, please like and subscribe, and maybe also check out my other videos. See you next time.